Hi everyone, my name is Jorge Chavez. I am professor at the University of Guadalajara, and at this time I will present you my poster titled Microstructural Analysis and Wear Resistance of Niobium area composite biomaterials processed by powder metallurgy. This work is about niobium, which is a biomedical material with an excellent biocompatibility and corrosion resistance, but it has a poor wear resistance, which limits its use in the device fabrication, which require high tribology or tribological performance, such as lobe bearing implants. Then in this work we try to increase the tribological resistance of niobium by adding ceramic particles, ceramic reinforcements, particles such as cerium oxide or ceria, which could improve the mechanical properties of niobium, and of course the tribological performance. So in this case the methodology of the work is using powder metallurgy technique, the conventional powder metallurgy techniques, which includes the mixture of powders for the composites. In this case we use 0, 1, 3, 5, 10, 15% of ceria added to the niobium matrix, which were mixed in a turbula. After the mixing, we compacted the powders using a stainless steel die. After compaction, we promote consolidation of powders using the sintering process in a vacuum atmosphere and 15,000 degrees. The sinter samples were metallographic prepared using the conventional metallographic preparation with silicon carbide paper and aluminum solution. After to obtain the mirror polishing surface, we etched the surface to reveal the microstructure. The characterizations involves optical microscopy, XRD, electronic microscopy, microhardness beakers, and wear test using reciprocating sliding tests using alumina sphere as a counterpart. These tests were dry tests, where test launch in dry condition. So the main results reveal that the sample without the addition of particles has beta microstructure, BCC microstructure corresponding to the beta niobium, which is combined with oxide peaks after adding the ceramic particles. This is a contribution of the ceria or ceramic particles to the matrix with oxygen. So oxygen is forming some cerium oxides or niobium oxides, which obviously increase with the amount of cerium in the lattice. So these reactions produce a certain microstructure. First, I would like to show you the main properties in this table. In this table, we can observe the density of samples, which for the sample without cerium addition, we obtained 95% of relative density, and the relative density decreased with the cerium addition because of the possible reactions we have mentioned before. So this decrease in density, in relative density, does not show an effect in the mechanical property in the hardness. For example, in this figure, we can observe that the cerium addition produce the increase in the microhardness of the matrix, because the creation of the generation of oxides and the solid solution hardening of the matrix. So we have a certain level of oxidation, so it's producing a certain level of hardening. On the other hand, in figure 3, we can observe the CM micrographs of the samples. We can observe the sample without addition of ceramic particles, that the sintering is very low. The sintering level is low because the high melting point of niobium, which indicates that the sintering temperature is needed to be higher. So this figure, the images in this figure does not present correctly the densification level, because the samples has very high density zones, but also has low density zones. So we can show these different zones in the microstructures. But the curiosity is the formation of oxides in the boundaries of grains, which are promoted by the amount of the cerium. So the main results of wear test reveal that all the samples produce a stable coefficient of friction after some pre-stabilization period. This pre-stabilization period is regarded to the stabilization between particles, between counterpart and the surface. So before the counterpart needs to overcome the asperities in the surface, which is corresponding with a value of COF or coefficient of friction of 0.2. After dividing this stabilization period, the curves increase to stabilizate into 0.7 of coefficient of friction. The depth the depth of the wear tracks are shown in figure B. So we can observe that as how the ceramic particle addition can decrease the depth of the wear tracks, also the weight of the wear tracks. So it's effectively increasing the wear resistance, which is also observed in the graph in the figure 4C, which present an important decrease with the highest amounts of additions beside the porosity created. So for the wear mechanisms involved in the test, we observed it for the sample without addition of ceramic particles that there is a predominant abrasive mechanisms, as the groups are observed in the sliding direction. Also, some addition of material is observed with a plastic deformation forming some crest hairs. With the addition of ceramic particles, we can observe a change in the mechanisms to the adhesive mechanisms from the abrasive to adhesive, which is indicating that the oxide particles also could function as lubricant particles, but these results are only advances of the investigation of a student. So we need to run some tests, some additional tests to confirm the results here. So thank you for your attention.